Hi, welcome to SurvEngCalc Part 5. And in this video, I'm going to be talking about superelevation. Superelevation is designed to ease vehicles into, around, and out of a curved stretch of road whilst travelling at speed safely. This is achieved whilst on approach to the curve by gently lifting one side of the road, the outer edge, and in this case pivoting upwards from the centreline axis. This is done until the outside edge is at the same slope percent as the inside edge from the crown. This is called continuous cross slope or continuous crown. From this point on, the whole road, that's both sides, will pivot or turn on the centre line upwards until maximum super elevation is achieved. And I'm just going to explain a little bit about what I've just spoke about there. Okay. Okay. So if we were standing here and our eyes were looking at cross sections all the way through here. We've got normal crown, which is this part here, normal crown road, which is there, and in this case, we've got a 2% slope going downwards there, either side from the centerline axis. This is the actual start. I'll just click onto this one a bit. This is the actual start of the super elevation here. This is from normal road crown, which is there. Um, We've got run out and we've also got run off, and this is dealt with a little bit differently little bit different to what a transition curve is done, because we've got a third of the runoff that goes into the curve and two-thirds that actually go into the straight. But I'll talk about that in a minute. But I'm just going to go through what we'd be looking at if we was walking through this in sections. So, okay, on here, if what we do is we'd be walking through, and the road would gently be lifting up on the outer edge until one side of the crown is actually level with the center line level there. So this would be at 0%. And then as we'd go through, we'd end up, they call it reverse crown there. I'll call this continuous crown. We've got a continuous cross slope of 2% going there. And then we would carry on until we reach full super elevation. Okay, we would go round the curve in full super elevation, keep going round until we get to the end of full super elevation. And as we come down, it would be the exact opposite of what we would have going in as the ramp in for a full super elevation. The ramp out is exactly the same. So we'd be coming through here. The road would be turning until we ended up with continuous cross slope there. That's where the road's at, the same as the normal crown there, but just going straight up as 2%. Then it'd be coming to the end of the runoff there, where we'd be having a 0% there, which the road would be flat on one side, and then we'd be coming out to on the run out to normal crown, which would be there. So I'm just going to get rid of that for a minute. We'll just have a look at this. So basically, we're going from here, normal crown, to where the road gets flat, 0%, continuous crown there. The whole road starts turning from there on the centerline axis until we reach full super elevation, and that would be continued on all the way round through to the other side as well. Okay, so what we've got here now is with a simple curve, we normally have a 1/3, 2/3 rule, where a third of the runoff is actually into the curve itself, and 2/3 is on the straight or the tangent there. So if we look here, this is point of curvature there, or we would know it as beginning of curve, or if it was on the exit side of it, that would be end of curve. So a third of the runoff actually goes into the curve there, 2/3 are on the straight. So what I'm going to do is I'm going to go through some quick calculations, just show you how we get this 1/3 and 2/3 and how we calculate the run out for a standard curve. Okay, so I'm just going to get rid of this for a minute, and then I'm going to have a look down here, and I'm going to bring up this one here. Okay, what we've got here is this top curve here is a normal simple curve there, and this one down here is a transition curve. I'm going to talk about that one in a minute. So we're going to go through a calculation here to get the 1/3 runoff into the curve and the 2/3 onto the straight here, and find out where the run out is and the continuous crown. So I'm just going to bring up a little calculation that I've done earlier. If I can Just come down here. Let's go into that one there. Okay, to get the runoff for a simple curve, we have to use this little formula here, which is 3.6 times E divided by G times this little proportional sign here. Okay, and that'll give us the runoff or runoff distance or length. Okay, where E is the rate of the full superelevation, so that's the full superelevation of the curve, and G is the maximum relative gradient. I'll show you what G is actually. Let's just bring that one up here. G is from where the starting point of normal crown there is this slope going up here. Okay, that is G. That's maximum relative gradient. Basically, it's the difference in height there at full superelevation from normal crown, which is going to be nothing. That bit there, and it's measured in slope percent going down there. That's maximum relative gradient. Okay, and we get that from that is dependent on design speed, which is here. So for whatever design speed you're going to get there, you're going to get the maximum relative gradient. That's in percentage there. We use those values there. Okay. So, oh yeah, and this bit here, this proportional sign, this is to do with the road width of the road. So basically, that's however many lanes you've got, you would put that into this calculation here, and that would give you a value to go in there. So say for instance, I was only using in metric, my lane widths are a 3.6. I would put 3.6 into there, and that would give me 1, because the total of that would just be 1. But you don't actually have to work these out. There are tables there where you don't have to worry about putting that in to get the actual width, to get this proportionate there. I'll show you what that is here actually. If I can just get it, which is there. So if I was using just one lane width at 3.6 meters, it would equal 1 there. If I was using a four-way lane divided by 2, obviously because we're working it out from the center line axis going out to one side, it's going to be 7.2, and that would give me a proportionate of 1.5 there, and you just keep going up there to get that. So if you didn't want to work them out, just look up these tables there. Okay. So basically, that's what W is there. So what I've used is I've used for the maximum superelevation 5%, the the maximum relative gradient I'm using 0.65%, and this proportionate comes to 1 there. So when I plug that in to this little formula, it ends up with 27.692. So if I go to here, the whole of S is 27.692. That's the runoff there. Now I need to put a third of S into there and 2/3 into here. And the way that I do that is to get a third, all we do is we take the 27.692 and we multiply that by 1/3, or 1 divided by 3, and that gives us 9.231 meters. So basically on our little curve there, 9.321 meters from the point of curvature or beginning of curve is where the third of the runoff goes into. So you just add that to the chainage, and similarly on the other side there, you would subtract that from the chainage to bring us back into a third there. So add it to the chainage there. That would give us the chainage of a third of runoff into the curve. Subtract it from the chainage of the end of the curve there. That would give us the chainage of a third of the runoff on the end of the curve there. So now what we need to do is find out where the 2/3 go in here along the straights on the beginning and the end. So all we do then is basically we take the whole value 27.692, and we would just subtract it from the end chainage of that of the 1/3, and that would take us out to here. So that would give us the change there by subtracting the whole of it from here to there to there. That would take us to there. And similarly, what we'd do is we'd add it to the change there to take us to the change there. So that would give us our 2/3 into the straight. Now what we need to do is to find out where the run out is there. So um, what we do now is we just click onto there. We don't need that now. So we find out where the run out is. I've got right now to calculate the run out is basically the runoff times NC divided by E, where NC is the normal crown rate, which is at the beginning of uh, at the beginning of the ramp in there. So that's the normal crown rate. I'm using 2%, and then we've got the rate of the full super elevation, which we know is going to be 5, and basically we'll plug those into the calculation, and that gives us a run out of 11.077. So that's the distance there. So all we do now is we'll just subtract that from the chainage of what we gained for the 2/3 going into the tangent there, and that would give us the run out distance to normal crown. And similarly on this side, we just add that value 11.077 to this chainage here of the 2/3 into the straight or the tangent, and that would give us normal crown rate there, which is the run out there. Now for continuous crown, it's dead easy because all we need to do is use the same 11.077, and we can subtract that on this side of it from the runoff to give us the continuous crown there. It's the same distance, and similarly on this side there, we just add that to the runoff 2/3 value there, and that would give us the continuous crown there because those are both the same. So basically, that is how we would put the runoff, the run out, and the continuous crown chainages onto a normal curve or simple curve. Now what we're going to do now is just have a look at a transition curve, and it's a lot more easier for this one. For the simple reason is the whole of the whole part of the curved area is fully super elevated, and we use the spiral for the runoff, the whole distance of the spiral for the runoff. So we don't need to do any calculations for the spiral because that is the runoff there either side. The only thing that we need to work out is the run out and the continuous crown. And I've actually used this for the SurvEngCalc Superelevation app or procedure within the app. So we're going to do work through a little example for that now. So we're going to go to there for a transition curve example to work out the run out is I've used the spiral to curve distance as 86.030. I'm using a normal crown rate of 2% and a full super elevation of 5%. So calculating the run out is basically the distance times the crown rate divided by the full super elevation rate gives me a distance of 34.412. Okay, so I know from tangent to spiral there, I've got 34.412 will take me to run out, which is there, and that will take me to normal crown rate there. So I'll subtract that from that chainage, that will give me that there, and then I can add it to this chainage, and that will give me continuous crown, and vice versa on the other side there. I can add that value to the chainage, the end chainage there, the spiral to tangent, that will give me the run out there, and then I can subtract the same distance there from spiral to tangent chainage there to give me continuous crown. And that's it. Basically, that's how you would work out the chainages for a spiral curve. Okay. Right. Now we're going to what we're going to do now is we're going to use the app to calculate the levels at offsets going around the curve. Okay, and it would be the same for both cases there. So it'd be calculate the levels for the straights and the curves. So and for the offsets as well. I'm going to choose the super elevation procedure there. Now, okay, the slope percent. The slope percent is basically the centerline slope going all the way around the curve. Okay, it's going to be constant all the way through. Okay, so we're going to find out what the slope percent is there. At the moment, I'm just going to put that in as 0. Okay, just going to move that up a bit. And then the offset out, when we're talking about out for the application, out is always the outside edge of the curve. So if you're looking up chainage, it's always going to be the outside edge of the curve. So offset out is going to be 10. And now I'm going to do an offset inside, which will be the inside of the curve, which is going to be 10. Oh, no, wrong thing. It's going to be 10 there. Chainage increment, I'm going to put 10 meters. No, actually, I'm going to just, for now, I'm just going to do half a meter. And I'll show you why in a minute. Now, the run out length, which is what we've already calculated, which is 34.412, I think. 412. The chainage, I'm just going to put 0. So that point there is going to be 0. That's the ramp in. And there. And I know that the run out distance there is 34.412. So now we're looking for a crown rate, which is just going to be -2, -2, and the level at that point there, I'm just going to put that as 0. Full super elevation start. Now I know that it's 86.030 plus the run out length. So it's runoff length plus run out length, which is it's going to be 120.442. And the super elevation is going to be 5 on the outside. On the inside, it's going to be -5. It already knows that. Now we're looking for at the end of full super elevation, which is going to be obviously on this, it's going to be the end of the curve there. So it's going to be the length of the curve, and in this case, it's going to be added onto that chainage. It's going to be 408.156, and the end is going to be, it just works out the rest of it for you there. So the rest of it's all worked out. Okay, I'm going to save that. I can call this back up at another date. So if I was to reset that, call it back up, it's there for another day. Now what I'm going to do now is just press Calc. It's going to take a second because I've got the increments set to 0.5. So half a meter increments all the way around the curve. And the reason why I've done that is just to show you we can find where the various elements are. So now, first thing I'm going to find is I'm going to find out where runoff is. Okay, so it should be at 34 meters, 34.412. So, and if you know that this is offset O is the outside, offset I is the inside. So at 34.412, where is it? 34.5. It's about there. 34.5 is that's roughly where the road raises to the start of runoff there. Okay, and the crown on the inside just stays the same as where it is. Then we're going to look for continuous crown, which should be at twice, should be 34.412 again onto that, so it should be 68.824. 68. There we go, 68.5. There, so near enough 69 meters there. So there we go. We've got a continual crown there. So that's our levels there. Offset in, offset out, continuous crown. And then it should be all the way up to full super elevation. Then we can find out on the exit, ramp out it should be continuous crown should be at near enough 460, if I remember rightly. 460 somewhere. Where is it? 460. It should be. There you go. That's it there. Continuous crown is roughly around about 460 there. So that's where that is there. And then runoff should be 494.186. 494. It's there. So that's where the road flattens out again then, and then we start coming back down to run out, which it should come back down to -2 either side. There we go, and that's it. Basically, that's putting levels either side of the curves. It'll do simple curves or transition curves. So what you have to do is just remember before you do each new calculation. Um, Obviously, you've saved it. Do a reset, then you can do a calc, reset, call up, and you wouldn't put 0.5 there. I just did that just to look for where the elements were, the run out, the runoff, and continuous crown were. So you're going to have that, and you're going to know that it's going to be in there. So it's going to be 10. It'll calculate a lot quicker now, and there it is there. So basically, that's it. That's it there. At 10-meter intervals, all your levels all calculated out, and obviously if you're going to change this, I'll do a reset, call up. You're going to change the road slope. Say, for instance, we put 2% there, put 2 there, okay that. But just make sure you click down in these boxes just to change the levels, and then you can do a calc again. And it's going to do 0.5 because I've forgot to change that. But there you go. That's at 0.5, but that's with a 2% incline all the way through. And again, we can reset, call up. I can change that to 2, and now I'm going to give it a level. I'm going to give it a level. I'm going to clear that. I'm going to give it a level, say 5 meters. Okay. This time I'm going to do 10 there. Clear that. So basically, at this point here, there I've given it a level of 5 meters, and I know there's an incline of 2% all the way around to the end, and this will calc out the levels either side respectively there, and that's it there. I mean, if you wanted to check where everything is, all you do is, like I did before, just set that to 0, put all your other information in there, and you can find out where all the changes are if you want to peg them out. But that's it, folks. That is Superelevation on the SurvEngCalc app. Thank you very much.